In today's lecture, we will start discussions on graph theory. Now, the question is, what is a graph? A graph is an ordered pair of sets. The first set is called the set of vertices and the second set is called the set of edges. However, this set of vertices and set of edges are not independent. Every edge corresponds to two vertices, which are called the end points or the end vertices of these two of that edge. Let me write down the definition formally. A graph consists of a set of objects V and the objects denoted by V1, V2 and so on, called vertices, and another set denoted by E usually, consisting of edges consisting of objects which we denote by E1, E2 and so on, consisting of objects called edges. Now, what is the connection between an edge and vertices? Each edge EK is identified with two vertices Vi and Vj. We will be writing this fact by now here we have to be careful and mention that this pair is unordered. That means, we do not consider the order as important here. So, it is called unordered pair. Later on, we may introduce ordered pair, and then instead of just edges we will have directed edges and instead of just graphs, we will have directed graphs or digraphs. But we are not considering those type of graphs right now, we are considering just graphs or undirected graphs, and therefore, an edge is associated to a pair of vertices. In fact, we will later see that it does not mean that the vertices has to be distinct. So, what happens if the two vertices are same? We will discuss that also. So, it will associate to two vertices which need not be distinct. So, let us look at an example of a graph. So, we have got vertices which we write as points on a plane. Let us name these points, call them V1, V2, V3, V4 and V5. Now, we start writing the edges. The edge E1 is in a way interesting, because the vertices corresponding to E1 are not distinct. E1 corresponds to the pair V1 V1. It is called a self loop. So, the endpoints of the edge E1 are not distinct. E1 will be referred to as a self loop at V2. Now, where is E2? E2 is an edge like this, then E3 is this, E4 is this. Now, we come to another phenomena, E5. Now, we see that we have drawn two edges in between V1 and V3. It is also possible, because when I am talking about the set of edges, an edge Ek is associated to two end vertices or end points, let us say Vi Vj, and there may be some other edge associated to the same unordered pair of vertices. These two edges will be called parallel edges. So, we write this as the edges E4 and E5 each are associated to the end points V1, V3. Thus, there are two edges connecting the end points or vertices V1, V3. Thus, there are two edges connecting the vertices V1, V3, namely E4, E5. These edges are called parallel edges. Now, let us look at let us draw some more edges E6 and then E7. Thus, we have got here an example of a graph, the type of objects that we are going to consider in this lecture and in some subsequent lectures. Now, we can take this the whole thing together and denote this graph by an ordered pair of sets, let us call it G, V, E, where V consists of the vertices V1 up to V5 and E consists of the edges E1 up to E7. This is our graph. Now, we will consider the same graph and discuss some more terminologies which are related to graphs. According to our definition, this is a graph. We can restrict our definition a little more and talk about simple graphs. A graph G VE is said to be a simple graph if it has neither self loops nor parallel edges. Sometimes we will prove certain results related to simple graphs, but for the time being we consider the graphs which may have parallel edges or self loops. Now, we talk about two important concepts related to vertices and edges, namely incidence and adjacency and degree. Incidence, degree and adjacency. When a vertex Vi is an end vertex of some edge Ej, Vi and Ej are said to be incident with each other or incident to or on each other. Now, let us look at the graph that we have here and see some examples of vertices and edges incident with each other. If we consider V1, the vertex V1 and the edge E3, they are incident with each other. Or we can say that E3 is incident to V1 or incident on V1, or we can say that V1 is incident to or incident on E3. Similarly, we can say that V1 is incident with E5, we can say that V1, E4 are incident with each other, and so on. Now, it is not difficult to see that if we are given a graph and we can pick up, then in that case we can pick up each vertex and check how many edges are incident on it. Now, that number is called the degree of that vertex. The number of edges incident on a vertex Vi with self loops counted twice is called the degree of Vi and denoted by dVi. So, we have talked about incidence, we have talked about degree. Now, the question is, what do we mean by adjacent vertices or adjacent edges? Two vertices are said to be adjacent if they are end vertices of a common edge. Now, again if we look at the graph above, we will see that V 1 V 2 are are adjacent to each other, because E 3 is common to them. V 1 V 2 are adjacent vertices, but if we consider V 1 and V 4, they do not have a common edge, therefore, they are not adjacent. V 1 V 4 are not adjacent vertices. Next, we talk about adjacency of edges. Two edges are said to be adjacent if they are incident on a common vertex. So, if we again look at our diagram, we will see that the vertex E 3, the edge E 3 and E 5 are adjacent, because they have a common end point or end vertex V 1. E 3 and E 5 are adjacent edges, whereas E 5 and E 1 are not adjacent. At this point, we have to remember another thing, that when we talk about degree of a vertex, we have to consider the self loops are contributing degree 2 to each vertex. The idea essentially is this, that suppose we are at V 2 over here and we have got a self loop E 1. So, it is coming out of V 2 in two places or coming in two places. That means, the edge E 1 is incident on V 2 twice, and therefore, because both the ends are incident on V 2. Therefore, when we are counting the degree of V 2, E 1 will contribute 2, and as we see from the diagram, E 3 and E 2 will contribute 1 each. So, the degree of V 2 is going to be 4 and not 3. Next, now we would like to see what happens if we sum all the degrees of all the vertices of a graph. Let us consider a graph with E edges and N vertices. Let us denote the vertices by V 1, V 2 and so on up to V n. Now, if we sum the degrees of all the vertices, we get a sum like this, d V I equal to 1 to n. Now, the degree of a vertex is the number of edges incident on it. Therefore, each edge for each edge we will get degree 1, the contribution of 1 to the degree of the vertex, and for self loops we will get 2, and the edge that is incident on a vertex, let us see like this. Suppose I have a vertex V and the edge E is incident on it. Now, this edge will have another endpoint, let us call that V dash, and so this edge will contribute another degree to V dash. In case this edge is a self loop, then this will come back to V itself, and therefore, it will contribute degree 2, contribute 2 to the degree of V. Because of this, we can say that each edge is going to contribute 2 to this sum, and therefore, this sum is equal to twice the number of edges. We can check this by examples. Let us look at one small graph. Like this. So, let us call it V 1, V 2, V 3, and V 4. Now, degree of V 1 is equal to 2, degree of V 2 is equal to 3, degree of V 3 is equal to 2 and degree of V 4 is equal to 1. Now, if I add all of them, degree of V 1 plus degree of V 2 plus degree of V 3 plus degree of V 4 is equal to 2 plus 3 plus 2 plus 1, which gives me 8. And now, if I count the number of edges, this is 1, 2, 3 and 4. So, the number of edges equal to 4. So, the sum of degrees I equal to 1 to 4 dvi is equal to 2 times the number of edges. That is 2 times 4 equal to 8. This rather simple observation has another interesting consequence, and that is the first theorem on graph theory that we are going to prove. So, we have this theorem This theorem states that the number of vertices of odd degree in a graph is always even. Now, the question is why, and that is what we will do when we check the proof. Now, suppose that I have a set of edges and number of edges is n. Suppose G equal to V comma E is a graph where V equal to V 1 up to V n and the number of elements in E is small e. Now, we already know that if I sum up all the degrees of the vertices, sigma I equal to 1 to n dvi is going to be 2 times of E. Now, what we observe that in capital V, that is the set of vertices, there are two types of vertices. The vertices which has got odd degree and the vertices which has got even degree. Now, let us write over here, let V odd is equal to the set of vertices with odd degree and V even is the set of vertices with even degree. Now, if we have this, then the sum that we are considering can be split up into two partial sums. One sum dVi, where this is over V odd and the other sum is again dVj, where this is over V even. We can write all Vi belonging to V odd and all Vj belonging to V even, and this is equal to 2 times E. Now, at this point we realize that this term is an even number. The reason is that each of dVj by definition is even, because these degrees are even, and if we sum up even numbers, no matter how many of them, we are going to get an even number, and therefore, we will have sigma Vi belongs to V odd d of Vi equal to twice E minus sigma V even d of Vj, Vj belongs to d even. This is equal to an even number. Now, since it is an even number, then the sum dVi, where Vi varies over V odd, is going to be even, an even number, but we know that individual dVi's are odd. Now, if I add some odd number many times, then I am going to get an odd number. So, the sum, the number of terms in the sum here has to be even, and that means that the cardinality of V odd is going to be an even positive I should write an even integer, non-negative integer, because of course it can be 0. This completes the proof of the theorem. So, what we have proved, that no matter whichever graph I take, and if I compute the degrees of the vertices, then we will see that number of vertices with odd degree will always be even. With this, we come to the end of today's lecture. Thank you.